Well, friends, welcome to the channel Total Output Power Solutions. I am Manohar Tattwadi, and in this session, in this video, we are going to learn about the steam condensers in the thermal power plants. So, this is a thermal power plant diagram of a 210 megawatt system, and you can see the condensers here. The steam from the LP turbine goes directly into the steam condensers. The steam condensers you can see here in this diagram. The means you can notice the position of the steam condensers. The LP turbine exhaust is directly connected to the steam condenser. So there are two condensers, or you can call it a twin condenser, and the condensate goes to CEP. The steam from LP, actually in the condenser you will see that the cooling water flow is first established, and then the steam from LPT enters into the condenser. So the pressures and temperatures here are shown. These are the design temperatures and pressures, and you can know the difference from the, you can take the actual readings and you can know the differences after that. Now we can check the total heat that is supplied and the heat lost in condenser. How much heat is lost in condenser? The heat supplied is in the boiler, and then the heat in the form of steam goes to the turbine, HP turbine, then again to the boiler, then from then into the IP turbine, and then into the LP turbine, and the LP turbine steam, it goes into the condenser. So the total heat is consumed by the turbine, and now it enters into the condenser. The prime mover energy is given to the generator, and which generates electricity. Here we can say that about means 1 unit or 1 kilowatt hour is equal to 860 kilocalories per hour. So if 1 kilowatt hour is generated, that is the output. Now the losses in the generator, the losses are mostly the I square R, and many other losses may be there. Very small amount of losses are there, but the I square R loss is as high as around 20 kilocalories. Then in the turbine, we take it as a whole turbine. The turbine exhaust, then there are some slight leakages, then maybe some heater change, or the heat exchange in the heaters, so heater efficiency, etc. All this, that amounts to around 1185 kilocalories. So the input to the turbine should be 2065 kilocalories, and that is we call as turbine heat rate. So 2065 kilocalories per kilowatt hour is the heat rate of turbine. Then this heat is being supplied by the boiler. So we'll consider the boiler losses. The boiler losses here are, we can see that they are around 331. So if you measure all these three, the heat losses will come to 331 kilocalories. So the total heat supplied will come to be around 2396 kilocalories per kilowatt hour. So if you want to generate 1 kilowatt hour, you will see that 2396 kilocalories of heat is to be supplied, and out of which 1185 kilocalories are generally spent in the condenser only. They are lost to the cooling water by the in the condenser. The total heat supplied, you can see heat lost in condenser is around 1185 kilocalories per kilowatt hour. So approximately 50% of heat supplied is lost in the condenser. Now the inference, what actually we can draw the inference from this. The condenser is the most important component that affects the turbine cycle heat rate, because 50% of energy is being lost in the condenser only. For condensing the steam, condenser removes heat of vaporization from steam and rejects it to atmosphere through the cooling water, or maybe some other maybe there air condensers may be there. So it depends, but it rejects to atmosphere through the cooling water. About 50% of heat consumption is rejected to the circulating water through the condenser. The typical condenser, this is one of the condensers. There are twin condensers in 210 megawatt, but the one condenser is like this. You have a circulating water inlet, you have a circulating water outlet. The circulating water is passing through the tubes, various tubes. There are various tubes in the condenser and it passes through the tubes, whereas the steam from the LPT is passing over the tubes, and then it condenses into the condenser hot well, and this condenser hot well is then transfers the condensate into the deretor through the condensate extraction pumps. In the TS diagram, it is shown there the point number 2 and point number 3, that is shown as the condensation. So this is a typical condenser. Then effects of condenser back pressure. Now we see that we maintain some back pressure in the condenser, means a vacuum in the condenser. So around, what are the effects then? 10 to 15 mm of mercury improvement in condenser vacuum, it leads to about 20 to 30 kilocalories per kilowatt hour. That is 1% improvement in the heat rate for a 210 megawatt unit. This estimates a coal saving worth of rupees 1 to 2 crore per year for a rail fed station where you are getting the coal from rail. So there it estimates around 1 to 2 crore per year in a 210 megawatt unit. Lowering back pressure always result in increased output? No, it doesn't always. So you should not lower the back pressure to after a certain value. So as the back pressure increases, if back pressure increases, certain losses they increase. So what are the losses? You have got increased CW pumping power, you have increased leaving loss, you have reduced condensate temperature, you get reduced condensate temperature and increased wetness. So optimization of back pressure is required for optimum gain in the heat rate. Now, effect of varying condenser back pressure. Here you can see the graphical representation of the same, and there is a optimum value, and you have to work for that optimum value. You have to go for that optimum value in the condenser, and you have to maintain that condenser vacuum or condenser back pressure. So now that is why the question of the discussion is about the performance optimization of condenser. Now, why performance optimization is needed? It is virtually a neglected component because there are no moving parts as compared to the rotating equipment. Then operation activity is limited to establishing and maintaining vacuum and starting and stopping of CW pump. Only two things are there: maintaining the vacuum, establishing the vacuum through the ejectors, maybe some ejectors somewhere used, and the starting or stopping of CW pumps. The negligence is based on mistaken priorities. Sometimes we have mistaken, oh, there is a tube leakage, but some other priority wise, some other problems may be there. So the mistaken priorities are also there, and that is why the negligence is there. The objectives of performance optimization. Now, what are the objectives? Condenser and associated system problems cause significant loss of heat rate and efficiency. Most of the losses are recoverable with the improvement in operation, maintenance, material, and design. The factors which affect the condenser performance are tube fouling, air ingress into the system, high condenser heat load, cooling water inlet temperature, and cooling water flow. So these are the factors those affect the condenser performance. Now the tube fouling. The tube fouling is there maybe because of some microalgae or something present in the CW through which the water is passing. So the tubes must be cleaned. So this cleaning, and that is why the tube fouling may be there because of this resistance to the water flow. So that therefore the decision of cleaning, condenser tube cleaning, is very important. Now cleaning of tubes, that cleaning can be done at part load or during the opportunity at a shutdown or maybe in the annual overall. Then fixing the limit for deterioration of vacuum into 10 to 15 millimeters of Hg. Means if suppose 10 millimeter of Hg it reaches, the vacuum deterioration reaches to 10 millimeters of Hg, you can take the decision for condenser cleaning. Now if you have a regular cleaning effect, then it is shown here in this graph. Suppose at 1,424 you have a set line. After overall you start the unit, and from there the vacuum deterioration starts. So in annual year 1,425 the vacuum would have dropped to around 30 mm of Hg, and the Heat rate therefore the increase to 75 kilocalories per kilowatt hour, because there is no cleaning of condensate, no cleaning or no overall. So if you take it in the middle 110 24, you take a outage and get the tubes clean, that time you will see that there is a significant difference. Again it will come down to around 3 millimeter, only deterioration will be only 3 millimeter of Hg, and then it may rise to only 15 of Hg. So there is a table also, and depending on this you can have some data, and the after that data you can have decide the tube cleaning schedule. The condenser performance, the condenser vacuum deterioration from overall to overall due to dirty tube is around 10 to 20 kilocalories per kWh if no opportunity cleaning is carried out. If no cleaning is carried out between overall, revenue loss will be around rupees 197 lakhs per unit per year for a 500 megawatt unit. Recovery of losses by cleaning at part load or during opportunity shutdown, vacuum can be improved by around 8 millimeter of Hg, that is 16 kilocalories can be recovered per kWh. Improvement in heat rate during the financial year is expected to be around 9 kilocalories per kilowatt hour, resulting in a saving of around rupees 54 lakhs per unit per year. The condenser tube cleaning techniques are there. You can have the cleaning done by a high pressure jet. Then there are some sponge rubber balls. They are online, maybe you can have them online. The condenser tube cleaning will be going online continuously. Then backwashing, the use of four-way valve. Here this may be done after taking a shutdown, and you can take a partial shutdown. Then water powered cleaners, and then chemical cleaning in worst case when the vacuum is deteriorated to a quite a great extent, that time you can do it, chemical cleaning. Then the another point is the air ingress or condenser air in leak, that is air ingress. So air in leakage adversely affects the condenser vacuum, heat rate and corrosion rate of the system. Air blanketing on the tubes severely affects the heat transfer. 1 layer of air equals to around 16 meter thick of copper. That is why it is very important that the air blanketing should not be there. So air in leakage should be avoided. The areas of air ingress are generally the LP turbine glands, then LP turbine diaphragms, LP turbine parting planes, maybe CEP glands, maybe of the standby pump. The running pump, there may not be any leakage, but air ingress, no chance of air ingress, but in the standby pump there may be chance of air ingress. Hot well as well. Then thermo driven BFP. If you have got a thermo driven BFP, then there may be some air leakage from that, air in leak from that. Wall glands, flange joints, etc. So these are the areas of air ingress. Then you can have a condenser air in leak test also, they can be carried out. Now online methodology, that is in how you can have the means air leak, detect the air leak. The increase in the subcooling of air steam mixture, then air steam flow at ejector or vacuum pump or the dissolved oxygen in condensate. So you can measure these three, and on that you can assess the air in leak, how much air is leaking. The condenser air in leak test, that also can be carried out. Then you can have the helium leak test also. So offline flood test during the overall. During the overall you can fully flood the condenser, and then you can check the leakages here. Then steam pressurization during overall, you can pressurize by means of some steam, and then you can find out the leakage. Or you can have online helium leak detection also. That technique is also there. You can have a helium leak detection. The number 3 is the high heat load. If the heat load is very high, then also this problem, that may be a problem for that. So high heat load may be due to poor turbine performance. The turbine performance is poor, the blades are worn out, or some other things are there. That is why the LP exhaust temperature is high, and that may be a cause. Then passing of high energy drains. Some drains are connected to the condenser, and if they are passing, then the load on the condenser will increase. Heat load on the condenser will increase. Installation of, now passing of high energy drains means you can install some thermocouples on the downstream side of the energy drains. so that you can know which drain is passing. Progressive replacement of high energy drain walls. The drain walls generally they are not operated, so the you can after some aging effect may be there, so you can have progressive replacement of high energy drain walls. Then attending the walls during the opportunity shutdown. Whenever you have opportunity, you can checking the wall passing before overall. Now you can before overall you can check the wall for passing, and then after means in the overall you can attend that. Joint checking by operation and turbine maintenance department after inlet startup. And maybe some low inlet steam parameters may also cause some high heat load. Then cooling water inlet temperature and flow. The CW inlet temperature maybe you have got higher CW inlet temperature due to poor cooling tower performance, or high lake water. If you have got a lake, then it is high lake water temperature that may be there, because of that the CW inlet temperature may rise. Then cooling water flow, you can have a low cooling water flow because of low pump performance, low intake level, or the tube may have choked. The now we see some terminologies that is there in this condenser back pressure. So vacuum in the condenser, that is vacuum in the condenser in mm of Hg. CW inlet and outlet temperatures, it is in degrees centigrade. CW flow design higher lower, that is in degrees centigrade. Heat load depending on the drains going to the condenser. Instrument errors, maybe some instrument errors are there, temperature, flow pressure, etc. TTD is the temperature terminal difference between saturation temperature of steam at exhaust and condensate out temperature, that is the TTD. CWDP is cooling water pressure difference at inlet and outlet of the condenser. So what should be our approach for analysis? You have a condenser back pressure high. If yes, then check the CW temperature higher than the design. If it is higher than the design, then the CT fan is not cooling water. If it is not higher than the design, then maybe the CW temperature rise is higher than design. Then if yes, then CW flow is low, or there may be high heat load because of drains passing. Now if there is a high heat load, then check up the CWDP, whether the CWDP is high, and if it is high, then there is a low flow because of high DP, and there may be microfouling in the tubes. If the DP is not high, then go to the CW pressure low, maybe the CW pressure is low, then the TTD may be close to design, and the high temperature rise, low pressure and normal TTD. If it is normal, then check the pump for the discharge. Then if the pressure is not low, CW discharge pressure is not low, then condenser TTD may be high, then check the instrument, or the high heat load may be suspected there. Similarly, if the CW temperature rise is higher than the design, their TTD may be higher than desired. So there can be an instrument error also in this case. So you can check up with that also. So this should be the approach for the analysis of the. So thanks for watching. In the next video, we will discuss about the calculation of the performance of the steam condenser. Till then, goodbye and take care. So please like, share and comment and subscribe to Total Output Power Solutions. I am Manohar Tatwadi taking your leave. Thanks. Thanks for watching.